I'd like to go ahead and introduce our speaker. Thank you for coming. Professor Thomas Bewley is here from UC San Diego in the Department of Mechanical and Aerospace Engineering. Dr. Bewley got his bachelor's and master's from Caltech and his PhD from Stanford. He works at the intersection of control theory, fluid mechanics, and numerical methods. But he has diverse interests, including environmental flow systems, robotic systems, SLAM mapping, and parallel computing. In fact, he's the author of the upcoming textbook on numerical simulation, optimization, and control.
Okay, thanks. Yes, so thank you very much for the invitation. Excited to see all the fun activity going on here. I think that thing just killed my computer. There we go. Okay, so first of all, why do dynamics control? Well, it's really fun. I guess all of you, when you were kids, did the balance the stick on your hand sort of problem. How many of you consider yourself controls folks? Can I see over half? Good. So you've seen the balancing stick problem, and you might imagine that if you have two sticks of different lengths, then you can move quickly to stabilize the smaller one and move more slowly to stabilize the longer one. If you, in front of the stabilization problem, if you solve a model predictive control problem, all you can do is move the cart back and forth. I challenged a master's student to do the double pendulum swing up and stabilization problem, which I've never seen solved before. He was really close. He had it in simulation. We had a really nice rig that he and another student built. I hadn't realized that he had given up his housing, and he was like a week away from his thesis defense, and he hadn't gotten going in the experiment yet. So I said, it was the hardest thing I've ever asked a master's student to do. I said, can you delay your defense by like 3 weeks? Because you're so close, I really want you to get this. And he said yes, but it turned out those 3 weeks he slept on the couch in the lab, and he got it, and I'm very proud of this result. So this is, if you don't find this fun, you shouldn't be doing this stuff. That's cool, all right? So that's dynamics and control. And so a first reason to get into this stuff is that, and the algorithms behind that, it's inherently nonlinear type problem. The algorithms behind this are successive linearization during the swing up using something called model predictive control, and simple successive loop closure is adequate. We used a state space H2 controller from the time after the swing up to infinity to stabilize the problem. So in addition to it being fun, dynamics, control, and state estimation are the enabling scientific underpinning of many really important problems that people really care about. And so that's why to do it. This talk will be divided into two parts. I'm going to start with a discussion of algorithms for coordinated sensor vehicle deployment for a contaminant plume forecasting problem. And then part two will be perhaps the more fun part, where we talk about the actual development of some new vehicles. So diving into the societal problems of societal interest, related to plume forecasting. I'm interested in things at the urban scale or at the scale of Southern California. Talking about the spread of wildfires, talking about chemical or radioactive or biological plumes that can happen due to accidents or terrorism-related activities, so of course the disaster in Tokyo, also the plumes that were released from Deepwater Horizon in the Gulf of Mexico. Yes, sorry, some of the slides are kind of dark. So the plumes that happened underwater in the Gulf of Mexico, also governed by the Navier-Stokes equation, is a very similar problem. I got stuck in Europe, not a bad thing, but I got stuck in Europe for a while because they shut down all the flights in Northern Europe because a volcano erupted in Iceland, not because it was sending ash all over Northern Europe, but because they didn't know where the ash was. And you couldn't see it from satellites. And so in problems of this class, certainly you can take pictures during the daytime. You'll know exactly where the smoke is from a wildfire. This is it's about a half mile from my sister's house in Austin. Fortunately, her house did not burn down. This is the visible part of the plume from Tokyo, and that's some visualization of where they guessed the oil was from Deepwater Horizon at some point, but they didn't really know. The issue is at night, where you can't see the smoke from from a satellite. If you're deep underwater where you can't see from satellite, or if you're in areas where the ash is so thin, you have to deploy vehicles in order to find these things. And so there are new technologies that make plume forecasting fundamentally a different problem today than it was 20 years ago. So we have off-the-shelf sensor and radio technologies, and we have the algorithms of weather forecasting and very powerful computer systems to drive those things. And of course we have the development of unmanned aerial, ground, underwater vehicles that we can deploy into these places where we have to get measurements essentially in situ. We have to go and explore through environments and get measurements. This is a picture of one of the projects that we were developing jointly with Los Alamos National Labs, where we were flying through smoke plumes that we were developing, deploying theater smoke near the ground and flying planes through it. A perhaps better experiment was one that we restricted to being happening on the ground. Let me talk about the results first, then I'll get into the algorithms. And so here is an experiment. We took a pot. Inside that pot is a smoke canister for essentially theater smoke. We were driving a bunch of vehicles. We'll talk more about the vehicles that we developed for this project. In the second half of the talk, I wanted to build up a fleet of these vehicles, and this gave me an excuse to. I wanted to run this parking lot scale demonstration of how you can track how a plume moves. So on the top of each of these vehicles, we have a off-the-shelf sensor that's actually designed for sailboats that can measure the X and Y components of winds. It's got a sonic anemometer, makes a sound, listens to it, makes a sound, listens to it between the three posts, and by measuring that the time that it takes sound to propagate, it can get wind measurements. Very nice off-the-shelf component. It also has a GPS, albeit not a very good one, built in, and a magnetometer. And we also have a particulate sensor on there. Each of these guys has a onboard board that can communicate through Wi-Fi to a local Wi-Fi network that we set up. We have an eye in the sky just for post-analysis of how well we did. The fundamental problem was, and this is the eye in the sky of it, this is me talking to some media crews. That's a graduate student, but the rest of these little white spots are a vertical view of those robots moving around, and here's our smoke plume moving around. And so we wanted to, at the parking lot scale, which is moving very quickly, it's a much harder problem than as the link scales get larger, things evolve more slowly. So things have to move really quickly to keep up with the motion of a plume at a parking lot scale just due to natural wind. The problem is to move these vehicles around to get to the information about where the plume is and where it's going, and to forecast where the plume will be some time from now. Say if there are populated areas, you want to forecast where the plume is going to move, and so you can evacuate people while not moving through the path of the plume. Yes?
First of all, the graduate student maybe is going to die. Right?
Yeah, he might.
You optimize for a number of controls. I mean,
the number of vehicles, that was optimized based on the number of slave labor, undergraduates that we could get to actually build the vehicles. So we built 12 vehicles. That's what we could afford to do. So this was a test with 12 vehicles.
Maybe you just needed 4 or 5.
So presumably, with more sensors, we can get a more accurate estimate. I mean, our estimate was lousy, and the more sensors we have, the better we did. I'd like to describe a little bit about the algorithms that we used, though. So certainly, more information is going to, and less noisy information is going to be better in a information deprived environment like this. There are two problems at play here, and so now I'd like to talk a little bit about the algorithms that we need to well, before I get into the algorithms, let me show you a picture and let me bring up the next slide, which helps me point out the algorithms. So again, the vehicles are moving around, the smoke is evolving, and we're trying to move the vehicles in a way that we can estimate the flow field and not just have them all dive into where the plume is. Perhaps this picture shows the algorithm a little bit better. So we have a truth model. So effectively, this is our mock-up of the parking lot, and our estimate. We have at the beginning, we have 100 computers running a 2D simulation, assuming the smoke is heavy and assuming the flow near the ground is approximately parallel to the ground. We're running 100 simulations or ensemble members in parallel, and if we take the average of all of those ensemble members, we get some estimate. At the beginning, it's decorrelated from what's really going on, and on the right side, once I start the simulation here, I'm going to show you some visualization of this uncertainty, which is maximum near the boundaries, and from one time step to the next, I'm going to show the vehicles moving around. I think I'm going to show them up here as well. The vehicles are the black dots in this simulation, and the information that I'm going to pick up from the truth model in order to provide to the set of computers doing a bunch of parallel simulations of the system and comparing and contrasting them in order to find the average and the covariance of the air is the only information that I'm going to pass from here to here is the information at the black dots that corresponds to the information that these guys can measure. So the wind, the two components of the wind velocity and the smoke density as a function of the trajectories as those vehicles move around. And so the vehicles move around according to the specification of the algorithm. And so there are two things going on in this picture. So the first problem that's solved is as the vehicles are moving around, I want to solve essentially a weather forecasting class problem. So I want to look into the recent past and I want to reconcile the measurements of the flow with the actual estimation of the system. So if the estimate is based on what we can observe in the measurements, if the estimate is off a little bit, I need to nudge, so I need to put an update term on the right hand side of my evolution equations. I need to nudge the evolution of the system in order to match the observed data. The second problem that I need to solve is I need to look into the near future in order to say, hey, where do I really need to send the sensor vehicles next? And I ask that question in a very rigorous way. What I'm trying to do is I'm trying to minimize the trace of the covariance matrix at the forecast time. I'm trying to minimize some clearly defined, mathematically precise statement of my estimation error over the region of interest. Now there are a few assumptions that you have to make. It's not a model-free setting, but I have a description of at some time. So if this is the current time, I have some time in the near future, and so at this forecast time, I want to minimize the trace of the covariance matrix, and I know that the observation that I'm going to make of the system comes from where the vehicles are between now and the forecast time. And so what I can do is I can use a model predictive control algorithm to optimize the trajectory of the vehicles between now and the forecast time in order to minimize the trace of the covariance matrix. And I can do that because the covariance matrix, not the estimate itself, but the covariance of the estimate, if I look in a linearized setting around my current trajectory, my current estimate of the state, the covariance matrix evolves in a way that depends upon what the C matrix is, where the sensor vehicles are, which affects the C matrix, and the observation, if you have y equals cx, where the vehicles are affects the C matrix, but it's not dependent upon the measurements themselves. So y itself does not come into your statement of your estimate of the state estimation error. So that means I can rigorously solve a problem looking into the near future and use a model predictive control type setting to minimize the trace of the covariance matrix at the forecast time by putting in feasible control inputs into the individual path of the vehicles. Yes?
So I didn't entirely follow what you just said, but I think My question is, why do the robots hang out in the white space so often?
So it's this is the counterintuitive part, which is why I particularly liked to show this video, is that what you need to know, especially in the setting that I have shown here, when you know where the smoke is coming from, essentially you know where the plant is in Tokyo, or you know where the broken rig is in the Deepwater Horizon. I know where the plume is coming from. What I need to estimate is the winds. I don't really need to dive all of the sensors into the smoke plume. So if you take a naive approach to a problem like this, it's like, let's fly all of these guys into the plume. And that's not really what you want to do. If you're trying to estimate where the plume is going to go, you want to estimate the velocity, the wind field nearby the plume, in order to get the maximum fidelity estimate of how the plume is going to evolve in the near future. And so it's a little bit counterintuitive, but in hindsight perhaps makes some sense. We had a bounded region here, and so another good question that you can ask is this a periodic box between here and here? No, not quite. This is a region inside a larger periodic region, and in the weather forecasting class problems, a typical hard problem that we haven't done particularly well here, but we recognize it as a fundamental issue to address, is how to handle the inflow and outflow boundary conditions on the four sides. It's a weather forecasting class question, and so it's the same question that you encounter in weather forecasting, and we haven't done anything particularly original regarding the boundary condition problem here. In fact, we haven't done it particularly well. The model predictive control setting, so I said for each of the vehicles as they're moving along, we're looking into the near future and going back and forth and looking, okay, what trajectory over the near future should those vehicles be moving in order to minimize the trace of the covariance at the forecast time. And that is running constantly as the system evolves. And so I was shifting my body as this was going, because time is evolving as I'm doing this calculation. So this calculation goes really fast, looks at a bunch of prospective trajectories of where these vehicles will go, and time is evolving as it goes along. So this is called a receding horizon model predictive control framework. We develop a trajectory for each of the vehicles, and then each of the vehicles goes to, say, the first of 5 waypoints on each of those trajectories, and then by the time it gets to the first waypoint, we've updated the trajectory a little bit, and we send an updated set of trajectories. If our comlink breaks down for a while, we actually send it several waypoints on the upcoming trajectory. It goes to the first, and then if it hasn't received new information from the supercomputer that it's in radio contact with, then it will go to the second or the third until it gets its updated set of trajectories, and it will go to those. And so it's a standard receding horizon model predictive control framework, but applied to minimize the cost function is minimizing the trace of the covariance matrix at the forecast time, where the covariance matrix is a function of the C matrix, and the C matrix is a function of the position of the sensor vehicles between now and the forecast time. Yes?
So you said that the C matrix doesn't depend upon the measurements.
C does not depend upon Y, right. Y depends upon C, but I can optimize the location of the sensors to optimize what the C matrix is in a linearized description of this problem, which is an important caveat, without knowing exactly what measurements I'm going to take between now and the forecast time to show how I'm deviating from the central trajectory that I think it's going to go on.
So at what point do the measurements affect? Because otherwise, if the measurements never affected that covariance estimate, then the path would just be pre-planned completely offline, right? So
the state of the system, so the system it's a nonlinear system, and so the covariance is a covariance of the estimation error around the central estimate, and the measurements definitely affect the central estimate.
Okay.
And so as the system evolves and I get more measurements, then I use standard extended Kalman filter, or in this case ensemble Kalman filter type feedback, and so that affects the central trajectory, and the central trajectory is what I linearize about when I'm doing this sort of stuff. So just to talk about the complexity of the problem then, because in the controls literature, it's very fashionable to work on a completely decentralized or overlapping decentralized setting where each of our vehicles figures out what to do just based on bird brains. And so they can only figure out very simple algorithms like dive into the plume, find or fly some isocontour of the plume. And I would argue that if you're deploying assets which are thousands, tens of thousands, or hundreds of thousands of dollars into real plumes, into radioactive plumes in Japan, or ash plumes over Iceland, you're going to be in some sort of radio contact with those vehicles, those assets as they're moving around. And so, since you're going to be in radio contact with those expensive assets deployed in a situation like this, then you might as well leverage a massive supercomputer sitting back at some NSF supercomputer site, and not attempt to solve a weather forecasting class problem on a Raspberry Pi class computer, because that's not a reasonable thing to do. And so, to illustrate how complex this problem was, I had, or my very good graduate students here, had a Wi-Fi network set up on this remote parking lot. So we didn't have internet access here, and so we had a computer set up, a local Wi-Fi network here, and not through a fourth generation cell phone, but through a 3G cell phone, my old Droid. We took all of the information from these sensors, picked them up twice a second. So we took a data point which had a location, a timestamp, a smoke measurement, and a wind measurement from each of these vehicles, packaged them up into a data packet that was received here, and twice a second it got the data from all 12 of these computers, packaged them up, and sent them over a 3G data link to a offsite supercomputer that did the simulation, and then that computer solved two problems. It looked into the recent past to do the weather forecasting class problem of, based on all of my measurements so far, what do I think the flow is doing? And I'll talk about that class of problem in a second. And it solved the second problem, which is called the adaptive observation problem, which is looking into the near future. Where should I route the sensors in order to do what I'm trying to do? In this case, minimize the trace of the covariance matrix at the forecast time, or some rigorous measure of minimizing my forecast error at some time in the future. How should I route the sensors to achieve that? And so all of that was handled through a 3G cellular data link, a single 3G cellular data link for 12 vehicles twice a second. And so if you're moving at a much if the plume is evolving at a much lower speed because you have a larger length scale, then the data transfer requirements are even less than what they were here. This is moving fast because it's a parking lot scale, which is a small scale compared to the larger scales that we ultimately want to deploy this at the urban scale. And so the point is, you don't need that much data transfer. And if you allow yourself to use data transfer to an offsite supercomputer, you have massive supercomputing capabilities, which are a whole lot more than a Raspberry Pi can do. All right. So now I want to talk a little bit about the problem of estimation and forecasting, because it's a fascinating question, and is where we've focused a lot of our work. Like I said, I'm not really a robotics guy. I'm a dynamics control guy. We happen to build robots because they're very useful for developing experiments that we can do nice dynamics control type problems on. So I want to spend a little bit of time here talking about the fundamental problem of estimation and forecasting, and I'm mostly just going to talk about it and not show equations, but of course there are some involved equations that back up all of this stuff. I'm going to talk about a new method for both the full estimation problem and for the approximate estimation problem. The full estimation problem is too hard to actually solve in practice. And so it's good to know what the right answer is, and to know exactly what the statement of the problem is for a non-Gaussian, nonlinear state estimation setting. And that will allow us to compare various methods. But ultimately, we have to solve approximate estimation problems. The most common, of which 90% of you are familiar, is the Kalman filtering setting, and there are variations on that that are important, and the most important one to know is something called the Ensemble Kalman method, which is what scales to high-dimensional problems quite well. And if somebody teaches you instead that you should learn the particle filter, hopefully by the end of this talk I'll give you my perspective on particle versus ensemble, but this ensemble method, which was actually developed in the weather forecasting community, not the controls community, but the ensemble method is a head and shoulders better method than this particle method, and I will get to my description of why that I believe that in a minute. Hopefully, can provoke some discussion, and then I'll talk about our tweaks to make some improvements to the ensemble Kalman setting. So first, I'm going to talk about the full estimation problem. How do you solve it? And so it's the correct answer, even if your system is nonlinear, and even if your estimation uncertainty is non-Gaussian. And so start off with an ordinary differential equation. So start off with dx dt is equal to some function, possibly nonlinear function of x. I'm going to call that nonlinear function on the right-hand side u, because I want to interpret it as a velocity, and u is evocative of that. So anyway, I have just dx dt is equal to u of x. That's my governing equation. So in order to track the uncertainty of a problem, so if I have, say, to make it concrete, say if x is dimension, has 3 states, so x1, x2, and x3. So for instance, in the example problem I'm going to show, I'm going to show the estimation of the Lorentz equation. So it's a nonlinear equation with 3 states. So phase space, then, if I look at a space of x1, x2, and x3, at any given time, if I'm at some point in phase space, I'm at some point in R3. And then as I evolve in time, depending upon where I am, the speed at which I'm going to move is exactly going to be in phase space. The speed at which I'm going to move from some location of phase space to some other location is exactly u of x. That's why I like to think of the right-hand side as a velocity through phase space. So then if that's my governing equation, then when I'm talking about the estimation problem is quite straightforward in the full problem. This was actually known before Kalman and Bewley did their work. This was known in the late 1950s, that the full estimation problem is, okay, I might be anywhere in phase space. I don't know exactly where I am. So I have to look over all of phase space. So if I have a 3-state ODE to begin with, then to estimate where exactly the system is, I need to look at a partial differential equation over 3 dimensions. So it's 3-state ODE, the estimation problem when trying to say where am I in phase space, becomes a 3-dimensional PDE. The 3-dimensional PDE it governs the probability P that I'm at some location X in phase space, and if I integrate P over all of R3, I get 1. With probability 1, I'm somewhere within R3. I'm somewhere within that phase space, right? And there are many locations in phase space that there's nearly 0 probability that I'm going to be there, right? So usually my probability is focused in a fairly small region in phase space. So I have a cloud of uncertainty in phase space, and so I have some region in X where P is non-zero. The integral of P over all of X is always 1, and the evolution of P in time is governed by the Focker-Planck equation. So for this equation, there's no diffusion, and so this sigma is 0. Sorry, so the probability stretches and convex according to an advection term like that, and then if there is a plus W, where W is some disturbance, then if that disturbance, under certain assumptions on the disturbance, if the variance of the disturbance is sigma, then there is also a diffusion term, and so if there's random disturbances acting on here, that acts to diffuse your estimate. So even if the right-hand side U is 0, if you have some localized estimate and you have some disturbances, then your estimate of where the thing is going to diffuse. So the probability is governed by the Focker-Planck equation. This was known in the late 1950s. And P causes, and this causes P, as I said, to stretch and diffuse. And so if sigma is small, which often it is, then this equation is nearly a hyperbolic problem. And so we have to march this equation in time. And as I said, it scales with dimension very poorly. So if I have a 3-state problem, then I need to look over a 3-dimensional phase space. If I have a 10-state problem, I have to look over a 10-dimensional phase space, and the problem becomes numerically intractable. So not very many people continue on this route, and many people need to try to approximate P in various different ways, and that leads to the several variants of estimation. But if you can have a big enough computer and a small enough problem, you can actually march the Focker-Planck equation on a grid, and you can solve the evolution of this thing. So between measurements, I like to think of the system evolving in continuous time, and then from time to time I take measurements. You can put things in a fully continuous or fully discrete setting. I like this mixed setting where I say, okay, my system is evolving in a continuous way, and from time to time I'm going to take a measurement, and so at the measurement time I'm going to have my prior estimate of what I thought P of x was before I take that measurement, and then I'm going to have a posterior which is going to take into account the measurement, and it's just an application of Bayes' theorem. The fundamental rule of probability is Bayes' theorem is the starting point. And so I march the probability according to the U of the governing equation and the diffusion from the right hand side forcing W, and then I update via Bayes' theorem and I go back and forth. That's all state estimation is. That's the correct full answer even in the fully nonlinear non-Gaussian setting. So the question is, how can I make that tractable, because this scales really poorly with dimension? And so pushing along the full Bayesian approach, I said, why don't we actually go ahead and calculate it? And so let me put a grid down over parameter space and let me march the evolution. Say I have a ball of uncertainty at time t is equal to 0. And so at time t is equal to 0, this could be well approximated by a Gaussian representation like you would ultimately use in a Kalman filter, where I have the center point is my state estimate, and I have a football shape uncertainty around that estimate. The eigenvalues are how big that football is in each of the 3 directions, and the eigenvectors are the direction of that football. And so that covariance matrix is a 3x3 matrix, has 3 eigenvalues, 3 eigenvectors, describes a football of uncertainty around that point, if we describe that as a Gaussian way. And if I were using a Kalman, or in the nonlinear case an extended Kalman representation, I'd restrict my description of that ball of uncertainty to continue to be a football. In this case, I'm running the Lagrangian equation for a short period of time. You can take a look at our Automatica paper that shows this from last year, and that has all the details of the simulation. But over a short period of time, with no measurement updates, you see you have a very non-Gaussian profile at the end time of this simulation. But you can actually run this simulation quite quickly, and the reason I can run this simulation quickly is because I started off with a focused amount of a focused region over which P was non-zero, and P was 0 everywhere. And so instead of calculating the PDE over all of R3 in this box that I show, which is 50 by 30 by 50 or so, instead of calculating the evolution of the PDE over that entire box, I mark which cells are active. I keep a list of active cells on a Cartesian grid, and I'm only calculating the evolution of this system on those active cells. So it's still a grid-based thing. It gives me the exact same result as if I had a grid over all of everywhere, but most of those grid points aren't doing anything. And so I'm actually not doing any computation out here, and I'm only doing computation as the system is evolving on those points which are non-zero and their immediate neighbors. And so that's how I can do this grid-based Bayesian estimation exploiting sparsity. The exploiting sparsity point is that it's grid-based, but I'm only calculating it where it moves. And that actually makes the solving of the full Gaussian, non-Gaussian, nonlinear state estimation possible in 3 states, maybe 4 states, but certainly not higher than that. So here's the same problem, but now with many measurement updates, but only of the vertical components. So say I have in this problem something that I can measure only the vertical component of the state. The state has 3 components, so I'm only measuring the vertical component. And so I'm narrowing it down vertically here, but the system might turn either way. So at the end time, my probability distribution function splits into two lobes. I can fully handle this with this sort of method. I can handle, and a Kalman method would completely break down here because you're assuming it's just a single football. And so it's nice in problems that you have a split like this. Maybe a later measurement will suppress, with a Bayes update, will suppress the probability here and boost up the probability here according to the later measurements. But if your measurements so far are just of the vertical state, you have a situation where your PDF can split, and so it's good to carry a method that can handle that. Now, what is the way that people approximate this? So this grid-based Bayesian estimation problem is hard. If you exploit sparsity, we argue you can do a decent job on it, and that's what the blue contours are, is our algorithm. But the way people typically solve this when they say, ooh, that problem's too hard, let me instead use what a fluid mechanics person would call a Lagrangian approach to solve this problem. So a Lagrangian approach to simulating a hyperbolic or mostly hyperbolic partial differential equation is, let me throw a bunch of points down where my system is initially non-zero, so in this cloud of uncertainty. Let me propagate the evolution of those points. And so that's what we're doing, and then we say, okay, near the end time, if I draw some cloud around those points, where those points are at the end time, then that's where my cloud of uncertainty is going to be. So I used a lot of computational elements in this particle simulation. You see the points are generally The points are generally coincide with what the correct solution is, the marching of the Focker-Planck equation. But you know, you have to really put tens of thousands of points into a situation like this to get to an accurate representation at the estimate time of what's going on. But that's not really the big problem with the particle filter method. The problem that I don't like the particle filter method is the following. The Bayes update, there's no really good way to do the Bayes update with a particle filter. So as you're marching your particles along, you start off distributing these particles effectively uniformly across the football, and so with equal probability, you'll be nearest to one of these particles in this Lagrangian-based representation of this PD of the Focker-Planck equation governing the evolution of the probability, and then at measurement times, if we're going to do measurement updates and apply Bayes' theorem, what we do, one way of implementing the particle filters, the other ways are equally bad, I think. But one way of doing the particle filter is you push down the probability associated with some particles, and you boost up the probability associated with other particles. And by doing that, you apply your Bayes update. And so you push down, you suppress the probability of those particles that are inconsistent with the measurements, and you boost up the probability of the particles that are more consistent with the measurements. And then you continue to evolve them according to your dx dt is equal to u of x, and then at the next Bayes update you do that again. But the problem comes up, it's called degeneracy. Some of these weights go to 0, these other weights get very large, and so what you have to do is you have to prune out those dead particles, and you have to take those particles that the weights are getting large and do some sort of ad hoc breaking them into multiple pieces. And unfortunately, for every group that's doing this, there's a different method for doing that split. But I would argue that every method of doing that split that I've seen so far, at least, is ad hoc. There's no really good way of doing that accounts for, if you've seen the Kalman filter, you have the Q, the covariance matrix of your state disturbances, the R, the covariance matrix of your measurement noise. There's no good way of doing that split that accounts for Q and R in a good way.
Tom, I have a remark on that, though.
Okay.
It's a parochial remark, and that is that there are techniques that some people might call natural for solving exactly this problem of impoverishment.
Impoverishment, resampling, yep.
This method called projection particle filter, where you, at each stage, when the evidence obtained by the particles just before update is condensed into some family, which is, say, exponential family, mixture family, and then when you do the Bayes update, you're using that family information.
Yes. So I'm familiar with that method, and that method is work. It is consistent, which means in the limit of an infinite number of particles, it converges to the answer given by the Kalman filter in the case of a linear system and Gaussian uncertainty. So it's a consistent method, and I agree. I can't say it's wrong. It's a correct method. But what I can say is that in all of the numerical experiments, at least that I've done, there is a method which is much more efficient with computational components, which is also a Lagrangian type method. Now I'm going to call them ensemble members rather than particles. But again, it's a Lagrangian based description of this mostly hyperbolic system evolving through this phase space. And the difference approach, and this was proposed by Evanson, a weather forecasting guy in the late 1990s, and it works in my experience better in every application I've seen the particle filter applied to. I think this ensemble method is a more natural idea, and most importantly, it scales with dimension in a very good way. And I'm interested in higher dimensional problems. And so again, we're going to put down a bunch of candidate trajectories that are going to march through phase space. Going to call them ensemble members now. But as I go through, I'm going to keep effectively the weight, if you like, associated with each of those particles. I'm going to keep them equal. And so at the measurement time, when I apply the Bayes update, instead of pushing down some probabilities and eventually leading to degeneracy and having to address the problem you just discussed, I'm going to keep the weight on each of the particles equal. And so when I'm doing the Bayes update, instead of adjusting the weights on each particle, I'm going to nudge in phase space the position of each of the particles a little bit. And if I do that in the correct way, and this is the remarkable result that Evanson showed, in the limit that you have a large number of ensemble members, you recover the answer given by the Kalman filter. So it's also consistent. So we have two consistent methods now. Particle filter is consistent when done in various different ways. The ensemble method is consistent when done these ways. So obviously the ensemble method doesn't suffer from degeneracy. What do I need this distribution for? That's a big question. What I need this distribution for is I need to get an estimate of the principal directions. So let's say it's not this bad. So let's say we're applying measurement updates. So we have a mostly quadratic or mostly Gaussian distribution, which might bend around like a banana a little bit. But we have a mostly Gaussian distribution of uncertainty. What I need of the covariance matrix, which describes the shape of this football, I don't need the whole football. What I need to do is I need to identify the principal directions of uncertainty of that covariance matrix. I need to find its primary eigenvalues because it's those directions that I'm going to update when I do an update, when I do a Bayes update. The directions that I have confidence about, I'm going to leave alone. So what I need the covariance matrix for is to identify those directions that I'm going to apply my update in. And the nice thing about this ensemble Kalman method is that as I'm marching these ensemble members through phase space, as opposed to the particle method, sometimes does a component of this, but as I'm marching these ensemble members through phase space, I'm going to tickle each of those trajectories with some right-hand side disturbances W, whose statistics are consistent with the assumed model for Q. And then when I do my measurement updates, I'm going to apply my measurement updates not with Y, the measurements that I actually take, but the Y that I use for each of my measurement updates. I'm going to nudge the position of each of these things in phase space. The Y that I'm actually going to use is going to be corrupted with a little bit of measurement noise, whose statistics are consistent with R, the assumed covariance of the measurement noise. And so I need a random number generator. It's a stochastic method. I need a random number generator to drive this process. But the upshot of it is that even if I don't have a distribution in those directions that are ultimately going to have the large locally up-and-off exponents, those directions that are eventually diverging, because I'm randomly exciting the problem with the correct W and V with the correct statistics as I go along at each step, that I eventually populate those areas. And so I get a distribution of candidate trajectories that well populates those rapidly diverging directions, the principal directions of the covariance matrix, so I can do my updates appropriately. And that is, in 10 minutes, the explanation of, in my experience, why the ensemble Kalman filter method scales with dimensions so much better than the particle filter method. Particle filter method, there is still a lot of people using, and I would like to engage with people in this comparison of the scaling of the two problems with dimension, because I think we're naturally, as controls folks, interested in problems with dimension higher than 1, 2, or 3. And in those cases, in my experience, the ensemble Kalman filter every time wins out. Maybe we can follow up on the discussion afterwards. So So as far as approximate Bayesian estimation goes, I've already discussed particle versus ensemble methods. I'm a keen proponent of the ensemble method, but I love to discuss it. There are also, of course, the Kalman filter, which is sequential, just marching forward in time. There are variational methods that in the controls community we call moving horizon estimation. David Main et al. In the weather forecasting community they call space-time variational method, developed by Talleyrand et al. And they're the same thing with some slight nuances, differences. But you essentially look over a finite region of time and you march back and forth over that window with state adjoint calculations in a similar way that you do model predictive control. So a key thing that we've done, and I'm not going to have really time to show the math here, but a key thing that we've done is we've developed the first consistent hybrid of the two. By consistent, I mean it recovers the correct answer in the linear quadratic Gaussian setting. It recovers the answer of the Kalman filter. And it's a hybrid because what we're doing is we're using an ensemble method, so we're marching a bunch of candidate trajectories through phase space. As we saw with those Lagrangian methods, we're using the ensemble method, so I call them ensemble members. And from time to time, we march the adjoint of those backwards in time to reinterpret past measurements in light of new data, to relinearize about a different trajectory. If we have a system which is diverging, we might initially think that we are turning to the left in the Lorentz system, but new measurements might indicate that we're turning to the right. If we just have a sequential method, if we have new measurements that say we're going over here, we say, oh no, I have to throw out my old measurements and essentially start from scratch. But if I have a mechanism in my method that's variational, I can revisit past measurements in light of new data, and I can relinearize my system about a path that turns the direction that I'm actually going, and so I can get a better method. So there's a motivation then to blend the idea of ensemble methods, which are very, very good at getting a low rank approximation of the principal directions of uncertainty of the covariance matrix, and a variational method which from time to time sweeps back in time and revisits past measurements in light of new data. So that's what we've done, is we've developed hybrid methods to do that, then building on the shoulders of those hybrid methods for state estimation, then we can also take our ensemble representation of our uncertain distribution of where the state is now and march them forward in time. And so I can propagate the covariance matrix in a low rank way by marching these ensemble members forward in time to get an estimate of the state of the covariance matrix at the forecast time. And then I can do this adaptive observation problem of optimizing the trajectory of the feasible trajectories of the sensors to make the best C's to minimize the trace of the covariance matrix at the forecast time. I can build a dynamic adaptive observation method using, again, a hybrid method that's based on ensemble members marching in time and sweeping back and forth in a variational type setting that builds squarely on the back of the hybrid method that's being used for the estimation problem. So these two methods, these two problems, when solved with these hybrid methods, are in essence dual to each other. And we've performed up to now mostly 2D numerical simulations which demonstrate the effectiveness of this idea. I think it's the right way of solving problems of this class and should extend to 3D as well. All right, I want to move on to other things because I know we have a broad range of interests here. We have some stuff going on in simultaneous localization mapping. This is a picture from the early 1980s of a cool Unix game, one of the first computer games called Rogue. You march through, and when you saw something, you drew a map of what you saw. Here's where you are, and you're moving, and you're seeing things. You're developing a math. The problem of SLAM is essentially that problem, but instead of marching through a randomly computer-generated world, you're marching with a real vehicle through a real world. This is a picture from the software developed at SPAWAR, which is, or used at SPAWAR, developed elsewhere, which essentially reproduces a 2D flat map. It uses a 6 scanning laser scanning around at ankle level, measuring where obstacles are, and just builds up a 2D map, which they build up in this crude 3D way, but it's really a 2D map. It's a picture like that. I think the time has come to solve problems like this, where we move not just one vehicle, but multiple vehicles through an environment. We take pictures of what we see. We stitch those pictures together. You might call it a 3D photo stitching problem to build up a VR of what you actually see with actual vehicles as you move through. That's a grand dream, but I think the technology is moving there by several different groups, and I think that's really the problem to solve. That's the, I want to deploy multiple vehicles and I want to have them collaborate. That's the hard problem to solve right there, is to build up a VR. And then you can explore that. Any firefighter or warfighter naturally knows how to take a look at that picture and get a view of the situation he's going to go into in a firefighting or warfighting, urban warfighting situation before he goes in, because every 20-year-old firefighter or warfighter has played Doom before and can go through and can explore something like that. Then they'll have a sense of what they're going in before they go in. That's quite valuable. We've been working in the lab. We've been taking baby steps, literally working on steps. I'm most interested in climbing stairs. We have some vehicles that are agile and can do that. And so we've been building up point clouds. The key thing that we're doing in collaboration with Yoav Friend, who's a big artificial intelligence guy at UCSD, is that we're taking the clouds of points that we get from stereo vision type systems, and we're mapping those onto planes, and especially a staircase have a known geometry, a rise, run, and two sidewalls. And so we're trying to estimate those planes and then where we are with respect to them and climb that. And so that's an essential part of doing robotic stuff. So that's the hard part. Now I just wanted to talk about some fun stuff. If I have to leave, I won't be offended. And so this was an exam question that I asked about 7 years ago now in my digital control class. Late night before the exam is like, okay, I just taught a class in digital control. Now we have to have some final exam. And so I dreamt up this question where if you take this toy, a child, it's called a pogo stick. Everybody's probably seen that. You take the child off and you put some box that has the capability of compressing a spring, and you put reaction wheels on the body, and so you can reorient the body in when it's midair for each bounce. And so then the question is, if you're bouncing here and you want to bounce over here, how do you move? Well, it's like it's a very fundamental problem. It's like the discrete time equivalent of the inverted pendulum problem. It's not a minimum phase. If you're starting out bouncing here and you want to finish bouncing there, you first have to move the foot to the left in order to move to the right, right? I mean, anybody who's bounced on a pogo stick has seen that before. It's very much like the inverted pendulum problem, but in discrete time. So it made for a fabulous final exam question. But then I saw that, okay, you could torque it, you could roll around, and you could jump and do all sorts of fun things. So I had 3 very talented undergraduate senior students say, look at this thing and say, we want to stay and do a master's degree. We want to actually build that thing. So at the beginning, we had no idea what we were doing. And then we started developing better linkage mechanisms that we actually patented. And finally, we came down with a design that actually has only 2 reaction wheels and a very clever linkage mechanism in the center, and so it can move this way to balance like a tightrope walker balances without deflecting this elastomer string in the middle. But when we move that way, we compress this elastomer string and create a force on the foot. So that sort of motion gets you the action that you do the hopping. You recover energy on the bounce because as the pull hits, the arms go down, compress the spring, and then they bounce back up and release the energy back into the leg that provides the energy for the next bounce. So left to right balancing is given by, again, motion like that, and fore aft balancing is given by spinning these wheels, which when you're driving around are just drive wheels, but when you're bouncing, you can spin those wheels and use them as reaction wheels. And so that's a clever, interesting design. Of course, hopping is a very inefficient mode to use on Earth, and so this is just of academic interest on Earth. But quite interesting if you go back and take a look at, and so for you space folks out there, if you take a look at how the moon guys went in your low energy things, hopping is the right way to move in a low G environment. You don't walk, you hop. And so if you're to deploy mobile rovers on the moon, a hopping mode would be a very interesting mode to look at, and that's where this would be useful, is not in 1G, but in like a 1/6 of a G or an environment like that. Sir?
Is there a clutch in there? Is there a clutch in there? No.
There's not a clutch. No, these are all direct drive motors. The key. The key is the linkage mechanism that really makes this work so well. There aren't any There aren't any clutches. Yes?
So is that opening, that's a passive degree of freedom, or there's a motor controlling the opening?
No, there's definitely a motor. And it's a fairly big motor. So we have motors to drive the wheels, and the motor is for compressing the spring is somewhere back in here. So yeah, you have these two things, and there's some gearing. I can point you to CADs which show how that works, but we actually built this and it works. So you have this switchblade design that we wanted to build a tank-like thing that was small, that could go under vehicles, and so you could do inspections at security crossings and things like that, but was also agile enough to be able to roll around in a V-type configuration, or even roll around on the other end of its arms in a C-like configuration, or even climb stairs. We've done all of those modes. We're working on the successive perching for climbing stairs right now, balancing on the edge of a single step at a time. The idea is that you keep the center of mass over the edge by moving the body, and so the treads stay at an approximate constant angle as you're going up. You're moving the body back and forth to keep the center of balance, the center of mass above the point of rotation on the edge of the step. So we're working on those modes with this. Again, this was used in our big plume experiment. We've got various social media presence if you want to take a look on YouTube. Let's just, this is the cool maneuver of it. Let me just jump to there. So Nick does this at trade shows with his back turned to the thing. It's a very reliable motion. It's not just a one-off movie. We've brought this to NI Week a few times, and many of you might have seen it there. And so we built 12 of these. After our plume experiments, we gave half of them to National Instruments, and so they go around and are showing off this single board Rio that this is built around, and the capabilities that has with that. Didn't mean to do that, sorry. So the next design that we've developed, again, we're a dynamics control shop, not really a robotics shop. So there are many spherebots that are out there. Most of them are essentially remote control cars inside beach balls. And there's a fundamental performance limitation with how a spherebot like that moves. And so as it moves, the beach ball has some mass and the remote control car has some mass. And if you move the remote control car within the beach ball, you change the center of mass to be somewhere than the center of the sphere. And so a component of gravity goes towards torquing the sphere. And that's how a spherebot like that moves. This does not move that way. There's a fundamental performance limitation, like I said, associated with directing a component of the acceleration due to gravity to turn the sphere of a RC car inside a beach ball. The center of mass of this thing is always at the center of the sphere. And so this fundamentally does not move that way. Instead, what we do with this thing that we call Ice Cube is we have 4 heavy gyros that we spin up. These are called control moment gyros in this setting because we spin up these gyros and then we gimbal their axes. So you use CMGs to point spacecraft. Many space people in here know about CMGs. So the guy who did this actually spent 6 years in the space industry developing these for pointing applications for telescopes and things in orbit. Then he said, okay, well, what about making inexpensive versions in ground vehicles? So this was our initial CAD, a mock-up like this we built. Then again with undergraduates, and the only way for me to tell which one's the CAD and which one's the actual build is the build has wires in them. So this is the actual build. The CADs, these kids can do these today, are just phenomenal. I love these things. So this is a 3D jigsaw puzzle. We have 4 spinning flywheels inside that we need to be able to gimbal back and forth, and then we need to have all of the other parts, and we actually built it and run it. It works. And so the idea of this is in the high school experiment, you sit down on a swivel chair, somebody spins a heavy wheel, and then you gimbal the axis like that. It takes very small torque here in order to turn you this way or turn you that way. And so now imagine, instead of just having one of those heavy spinning wheels, you've got 4 of them, and you can gimbal them in coordination with each other. You get a spherical vehicle, and that can with a small, so you can spin up these flywheels slowly with small motors. You can gimbal them with low torque with small motors. But if you spin up the flywheels to 5,000 or 10,000 RPM, then you have very high G onset, and you can get a lot of torque out of this. You can exceed the fundamental performance limitation of the RC car inside the beach ball. And so with a vehicle like this, I envision the application for this being a curious application, if you imagine you're some country, North Korea, I don't know, some country where you have to you have to get some information near a shoreline, and so you have some SEAL team come in and deliver underwater this thing, so you can make it buoyancy controlled. I'm not good at buoyancy control, but I know Derek is. You can move the thing up or down. So you can move it near the surface or near the bottom, and it's self-spinning, right? It's got the mechanism inside so it can torque itself and it can spin. It's remarkable that it can do such a thing, but it can. And so you can spin it near the surface or you can spin it near the bottom. Of course, if you spin it in the center of the water column, it's not going to move anywhere. But if you spin it near the surface or you spin it near the bottom, then you will move along. And then you can move, when you're going through the surf zone, you probably want to go to the bottom because otherwise you'll be thrown a lot. So you descend, you spin along. You can go through the surf zone, over the sand, over vegetation, through barbed wire, and upstairs with this. Name any other vehicle that you can build this size that can go through that range of motion. The reason that you can do that is that this is just a sphere. It doesn't have any external parts to get caught on stuff. And so I think it's a unique design which is very interesting for a unique type of mission. And then you do reconnaissance with it or whatever. We've built some dynamometers, small ones, regular dynamometers. It's open source. You can build it very inexpensively for a few $100s. You can characterize motor driver motor gearbox combinations. We're doing model-based control. These things weren't available, so we designed one. You can use these things. Of course, enabling technology that students currently have that we don't, that you guys are just, this is an awesome time to be doing robotics, is because you can get these things for $1,000 now. And so any good hobbyist should have these things in their garage. Anything that you can dream up in SolidWorks you can build. Couldn't do that in my day. You guys you really have quite an opportunity. One of the enabling things that did for us is we had a project in what I called the drawer of shame, a project that 3 PhD students had picked up and put down they couldn't solve. A struggling master's student who was barely a B student, but was gifted in using SolidWorks and using these emerging 3D printers, and could visualize things in 3D, said, okay, what's the problem? So I have a self-riding Segway basic configuration, something we call a MIP, or mobile inverted pendulum. So it's just got 2 motors, but we shaped the substructure of this thing so that when it rolls over a ping pong ball, the ping pong ball gets pinched between the body and the wheel. As the wheel turns, the wheel lifts and rotates the ping pong ball and can store a number of ping pong balls in this body, and then it's rolling around like a Segway. So from time to time, it can lean back, release a ball into this track, and huck it like that and throw it like a lacrosse thing. So that's a patented design. Once we started doing things like this, it's like, okay, we got to start talking to the toy industry. Well, first of all, our Gizmodo, our YouTube video got picked up by Gizmodo and got 50,000 views in one weekend. It was like, okay, there's some fun in this. We can teach with this. We can teach the problem. So I developed a new course. We build this thing called a MyMIP, which is for a digital control course using a digital computer. This is an Arduino Nano. We have some motor drivers here, an accel, a gyro, and a Bluetooth module at the top. Of course, the all-important bliffnars. Every robot needs a bliffnar, a blinking light for no apparent reason. You have to have bliffnars on any robot, right? So anyway, to teach a course about how to use digital control to control a continuous time system, this is a perfect platform. In this class, I had 43 students. Each student got a kit of $130 in parts and built this up from scratch. And then their oral exam at the end of the quarter showed me the thing working to various degrees. Most of them had it working. And many of them even had, Tipsy here, even had the Bluetooth working as was driving around. And they did that in a single quarter from scratch with a breadboard from Radio Shack and all the parts and assembled it. But a big pain in the neck was the encoders on the backside of these cheap motors. You had to mount these encoders and handle the encoders themselves. And assembling that wasn't particularly useful. It was just a pain in the neck that had to be done, but it was a part of the curriculum that I didn't really like. They all also have Bluetooth. Ultimately, I want to be able to have lots of these vehicles and run them around in an overlapping, decentralized way, and so we can do interesting projects that would obviously have relation to swarms moving in reality. But I want to be able to afford and get lots of vehicles. Can you turn off that thing now?